I'm Giorgio Metta. I'm from the Italian Institute of Technology, a research institute based in Genoa, Italy. And I work on human robotics. And in particular, I'm the coordinator of the ICAB project. Today, I'm going to speak about the ICAB, Human Robotics Project developed the Italian Institute of Technology. Then we wanted to see what happens if we exploit continuity in time. And these are a number of plots that basically show that the more you add data points, the better you are at recognizing objects. So for a robot, it can in fact observe the environment quite naturally and collect a lot of images before taking a decision. If you asked, or if the robot is tasked to actually grasp a cereal cup or a cereal box, it can actually observe while it's getting closer to the cereal box. It can observe from different points of view, so there's plenty of information to be acquired to make sure that's the cereal box and it's not a coffee or whatever, another thing. And this is shown in these plots that basically show that the more images we can actually use, the better the result. In fact, and these plots are against, again, the number of objects. And we see, for instance, that we can easily obtain 90% recognition quality over the 28 different categories of objects, which is a good result. I mean, this something was unbelievable, I think, a few years ago. So things are working well. And this doesn't even exploit the 3D structure of objects, so the robot doesn't know anything, it's just appearance-based, doesn't know anything about the geometry of the object itself. This other test is about the incremental learning. So tests that are done one day and then tested on the other day. We present different scenarios. So we train and test on the day we trained is one possibility. We test also on past days, so to see what happens. So we train on all possible days up to the current day, and then we test on the current day. Or we test on the future days, which means we train on the past, and the test future means the current day, without further training. So that's more difficult because it's all past data. If the conditions, for any reason, conditions change, like illumination, then the new data may not be so relevant for what you train for. But nonetheless, it performs quite well, as is shown here. And again, we managed to obtain an increase in performance day by day because you add more data points, and so performance increase, as shown in these plots. This can be combined with the ability of the robot to take more images for recognition, which has not been done in these plots. So the two of them are not combined on the other. So the next question we like to address, which is not something we've done, what happens in a week? So we start collecting data for a week rather than 4 days, and what happens? Or how's the performance, or how performance degrade if you train for 4 days and you no longer train, and you continue testing the system in different days, or in a month? That's another interesting question. So in this video, we show the training and object classification capabilities of the robot. As I said, it's an interactive technology where the robot interacts with the person that is showing objects, and the person speaks the names of objects. They get associated to what is being seen, and the robot can take a snapshot of the object together with the label, and can collect the data in this way. And this shows that the initial training stage, let's say, and the fact that the robot doesn't require collecting images separately from the labeling of the images. This all can be happening through human-robot interaction. The continuation of the video is shown in a sort of accelerated way, the training for 25 categories. And also the plot shows the probability that the actual object that is being observed in that moment is the object that is recognized. As you can see Here, there's a simple interface where we're asking the robot to recognize an object in the image by clicking on the object, and the bar that corresponds to the probability of that particular object being recognized is always the higher. What the robot is also doing here, you see that the probability grows higher and higher, and the reason for that is that the robot can observe the object for a number of frames, so it can be more certain that the object under observation is actually that particular category. And that's basically how the system works at the moment. Just to say that a system like this, it wasn't doable a few years ago. So this is basically the result of improvement in machine learning, improvement in vision, improvement in general, also in the speech recognition systems. So it's something that is getting along nicely because of improvements in various fields, including the object recognition system that we implemented. And we sort of, now for the first time, we're reasonably certain that this is leading towards something that's very, very reliable. So the problem with older systems was that they got confused quite easily, while this one is fairly robust. I mean, we present objects with any orientation, and even from very few samples, so very few images, so that object will recognize it well, which is far from obvious. And the training here is happening online, again, which is one of the requirements in robotics is always be fast. You cannot wait, hours to get an answer a specific problem. And in the continuation of the video, we show again the task where we simply asking the robot to point at a given object. It can be the sponge, as shown here, or the cube, and the robot will point at the object and ask for confirmation again, which again, as I said earlier, allows for increasing the training set. So incrementally, you can add more data points to the classifiers, so you can improve performance over time. And okay, now we move to another problem that is related to artificial intelligence, but also to the object recognition and to the use of tools. So the first slide shows two examples of objects that they're not only visually, let's say, distinct, but they can also behave differently. In particular, we've taken, two simple things. There's a toy car and a sort of a bottle, a cylinder, and the point is that the behavior of these two objects changes if you touch them. They tend to roll in certain ways, and in particular, the toy car will always roll in the direction of the wheels because that's a natural, it's given by the physics of the object itself. And the bottle will tend to roll, let's say, along at the right angle with respect to the elongation of the bottle. Again, because there's a natural rolling behavior. Depends how hard do you actually hit it, but normally that's a behavior. If you take a ball, for instance, doesn't matter. However you touch it, it will roll. So this is the type of behavior we were trying to elicit from the objects, just to try to make the robot automatically acquire, let's say, this type of behaviors and exploit it in case it's needed. So the plots in these slides and the following actually show the results from a bit of machine learning. Again, the same methods we used before, just reused here, that from simply having the robot play with the objects, as is shown in the videos, detect what is the main behavior of these objects. These plots are representations that basically show the direction of impact with the objects versus the direction of movement of the object. So how much it moves. If I take a toy car and I push sideways, it doesn't move much. If I take a toy car and I push from the back, it will tend to go for, I don't know, centimeters, meters, whatever. And that these three plots, in fact, are consistent because they show that the toy car is mainly pushed from a direction angle that is 0, which means from the back, or from 180, which is basically from the front. Vice versa, or almost the opposite for the cylinder, and it doesn't matter much how you push a ball, it will tend to roll. It will stop by random reasons. It's not necessarily that it stops because of, will stop for friction, but I mean, doesn't necessarily correlate it with the direction of pushing. There's another thing that we wanted to do connected to this, and it's shown in this other video, and is collect information about the use of tools. So if I have a toy car that is too far away for the robot, but the robot has a tool available nearby, you can grab the tool and reach the object, despite the object being far away. This is a behavior, for instance, that has been observed in many animals, and it's sort of a hallmark of intelligence, in the sense that it's figuring out that tools can be used for certain specific tasks. For instance, monkey use sticks to find ants for eating, and we like the robot to be able to do the same, use a tool to get an object closer or to touch an object that is too far away. So if you can bring the object closer, you can also grasp it. If you can just use a stick for pushing a toy car, you manage to push it no matter the distance from the robot. In this video, we show how the robot acquires information about the size of a tool. For doing that, we basically have to learn a new kinematics, because the tool extends effectively the size of the robot. And that means that in order to generate movements, you have to consider that the end point of the movement is not a hand, but it's the tool tip, so which requires different type of movement altogether. You can also learn, apart from the size of the tool, you can start learning the behavior of the tool. There's an example here, a plot, that shows how much a tool can be used for pulling something closer. So if the robot has a set of tools and some of them are useful for pulling, like a rake, a little rake, then we like to discover that. And that can be done from experiments again and using machine learning. The robot can try until it gets enough information for understanding that if you have an object and put a rake on top and you pull, the object gets closer. If you put the object if you put a tool by the side of the object, then it may not work. So there's a specific position you have to place your tool in order to be effective. That's what we explored here, very simple. And that's interesting in robotics in general, because imagine you have a set of tools you've never seen before, like screwdrivers, hammers, all possible tools that are useful for people, then can also be used by a robot, by a humanoid robot especially, and they will increase the ability of the robot to doing things. I mean, using a screwdriver is very useful, otherwise you cannot unscrew a screw. It's not doable simply. Using, even tools like these can be useful because the robot has a limited workspace, and so using a rake can be nice for reaching outside the workspace of the